Today I will discuss the energy gain in a free electron laser. In my last lecture I introduced free electron laser as a very fascinating device that produces tunable, coherent, high power radiation at the expense of energy of an electron beam. And now we would like to make some estimate of how much energy is transferred from electron beam to radiation. We shall discuss the following issues: the ponderomotive force that is exerted by the Wigler magnetic field and the radiation signal on the electrons, and that causes bunching of the electrons in the retarding phases of the ponderomotive wave. And then we would like to learn how the electron energy and phase of the ponderomotive wave as seen by the electron evolve in time or in space as the beam travels. We shall also discuss electron trapping in these potential energy minima and have some estimate of energy gain. Well, let me revisit a few things. We considered the propagation of an electron beam in a Wigler magnetic field, and a Wigler magnetic field had lines of force like this. This was vertical magnetic line of force. This is perpendicular to the plane of the paper. This is downwards. This is like this. This I call as the helical Wigler. And magnetic Wigler has a magnetic field given by Vw is equal to some amplitude Aw x cap plus I y cap into exponential of I kw z. This is called a right circularly polarized Wigler, and we are launching an electron beam into the system like this with a velocity v0, and I call the direction of beam propagation as z-axis, like this is z-axis. I can call the vertical direction as x-axis. So, when the electron beam travels through a Wigler magnetic field, it acquires a velocity that we deduced last time, which turns out to be equal to Vw is equal to charge of the electron, magnitude of the charge of the electron into Bw upon m, mass of the free electron, rest mass of the free electron, gamma 0 into Kw, where gamma 0 is the relativistic gamma factor related to electron velocity V0 by this relation. Gamma 0 is equal to 1 minus V0 square by C square to the power minus half. This is an important quantity. When the electron velocity approaches C, gamma 0 is quite large, and that is the case of our interest. So, the Wigler velocity these days that the charged particles can acquire Wigler velocity could be comparable to some fraction of C. And in addition to the Wigler, we launch an electromagnetic wave called seed signal or laser signal. So, what we have a laser signal that we want to amplify, we have an electron beam, both are launched into the Wigler region. This is my Wigler region. So, this is my Wigler, and I expect that there will be large output here. The laser signal should get amplified. The laser field that I wrote down last time was of this form. Let me write down on the next sheet. So, the laser field was something like EL, which was left circularly polarized, x minus Iy exponential minus I omega t minus kz. this is a purely transverse electromagnetic wave with phase velocity omega by k almost nearly c. No electron can be in phase synchronism with this wave because no electron can move with this velocity. It is a fast wave device in which omega by k is close to c, and that is inaccessible. This velocity is inaccessible by any charged particle. This wave also has a magnetic field BL, which is equal to k cross E from Maxwell's equation upon omega. And if you simplify this, put the value of k as kz cap and simplify this expression, it turns out to be equal to I k upon omega into EL. So, your laser has electric field and magnetic field. It imparts an oscillatory velocity to electrons also, which turns out to be VL, which is equal to charge, magnitude of charge of the electron into the laser field upon m, rest mass of the electron, iota gamma 0 into omega. This is the electron velocity due to the laser signal. If the magnetic wiggler is not there, but because both the wiggler and laser are present simultaneously, the electrons experience a force due to both of them called Lorentz force, and that force is important. Let me write that force as F P, is given a name called ponderomotive force, and that is caused by the interaction of, well, this is minus E into V cross B. This is called the Lorentz force, in which this is due to the wiggler and this is due to the laser. And there is another term minus E, V due to the laser and B due to the wiggler. Well, it is implied in here, but let us understand the origin of this. When the electrons are travelling in this direction and they are seeing an electromagnetic wave, then the electrons are acquiring a velocity, suppose perpendicular to the plane of the board, this I call as VL at some place. And somewhere at some instant of time, the magnetic field due to the wiggler is BW. They are perpendicular to each other and their cross product will have a direction. This is the direction. So, this will exert a force along the direction of propagation of the beam, VL cross BW, because both are transverse forces, transverse quantities, and hence their cross product will produce a Z component of Fp. Same thing happens because of this velocity, sorry, this is this term. Similarly, this term also happens the same way. The electron velocity due to the wiggler is VW and the laser magnetic field is like this at some location, at some time. They also contribute to Fp in that direction. So, these two forces are in the direction of the electron beam. It has a great advantage. Number one, that this force is in the direction of V0, the original electron velocity, and hence this force can retard the electrons and gain energy, or this radiation, which is essentially the dominant term here, can gain energy from the field. Out of these two terms, this term turns out to be stronger, this turns out to be weaker. So, this is the dominant term, and I can ignore the other one. For the sake of completeness or exactness, one can retain the other term as well. However, for us this should be all right, that I will retain only this term. Here one should remember one thing, that when I multiply velocity and magnetic field, then I am really talking about real quantities. It is a real, because in our representation we have expressed these quantities as complex numbers, complex quantities. but actual velocity of the particle is not a complex quantity, it is the real part of the complex quantity, it is implied. Means this Fp primarily is real part of minus E Vw and real part of B L. This is important. Re symbolizes real part of a complex quantity, and if one uses a complex number identity which says that if there are two quantities A 1 and A 2 and you want to multiply their real parts, then this can be shown to be exactly equal to half real part of A1 cross A2 plus A1 cross A2 star. Star means complex conjugate of the quantity. One can verify this by considering A1 to be A1 plus I times A2, where A1 and A2 are real quantities, and similarly A2 you can write down as B1 vector plus I times B2, where B1 and B2 are also real quantities. Just substitute these in this equation and you will verify that this identity is satisfied. I would like to employ the same identity to evaluate this product of real parts of two complex vectors. And once you do this, you obtain the Vondermotive force Fp to be equal to minus E by 2 and real part of Vw cross Bl. The complex conjugate term in which Bl star is there does not contribute because the real part turns out to be 0. This is the only term that survives. And when I put the values of these quantities, the expression turns out to be, put the value of Vw and Bl, and it turns out to be minus E by 2 E upon m gamma 0 Kw, this is the value of Vw magnitude, multiplied by real part of, you will get here Bw coming from Vw cross El into Ik upon omega, and simplify this expression, it turns out to be equal to minus Ap into cos omega t minus Kp z, where Ap is equal to, the quantities from there you get is equal to E square Aw Al into K divided by m gamma 0 Kw into omega. So, this is a force that acts on the particle in the z direction. This is in the z direction. Amplitude is Ap and it has a phase term here whose frequency is omega, but wave number is Kp, and Kp is the sum of laser wave number plus Wigler wave number. You may recognize here that the phase velocity of this force, which we call as Vp, is defined as omega upon Kp, which is equal to omega upon K plus kW. Since omega by k is c, this quantity is less than c. This may be just smaller than c, but certainly it is less than c, and hence it is possible for the particles to respond to this force resonantly, and that is the beauty of free electron laser, that this quantum force can resonantly interact with the particles. The amplitude of this quantity is proportional to the amplitude of the Wigler field. It is also proportional to the amplitude of the laser field. Obviously, in the device, laser amplitude evolves as the laser travels. So, one has to be careful in examining the energy gained by the laser, that this force will retard the particles and the force amplitude will also go up. These two things should be taken into consideration simultaneously, self-consistently. However, a lot of information about energy gain can be received, can be obtained by treating AL to be constant for a while. So, let us examine the response of electrons to this force. This force will give rise to, will influence the Z component of equation of motion. What I can do, if I move to a frame of reference, go to a frame moving with the velocity of the quantum force, moving with velocity Vp in the z direction. Suppose I go to a frame in this direction, then the quantum force will appear like Fpz, will appear as minus Ap cos Kp z prime, where Doppler shifted frequency of this force is 0, because it is moving, the frame is moving with the velocity of the velocity of the force, and this is the Lorentz transformed wave number of the force. This sort of expression you will get. Now, in order to appreciate the particle motion in such a force, let me draw a figure here. I will plot Fp as a function of z prime. Plot Fpz here as a function of z prime. What you will get is that, suppose the maximum value of Fpz is Ap. So, plus Ap minus Ap, I can put some 9s here. Suppose this is Ap and this is minus Ap here. What I can do, if I plot this, it will have a periodic variation like this. You may note here that at some values of z prime, Fpz is positive, and other values of z prime, Fpz is negative. The regions of values of z prime for which Fpz is positive, those regions are called the accelerating zones. So, this is positive here, so I will call this as the accelerating zone, and this region I will call as retarding zone, because Fpz is in the reverse direction. This is the force experienced by the electrons due to the combination of Wigler and laser fields. Now, what will happen? If I choose the initial electron velocity, when I launch the electron into the Wigler region, V0 slightly bigger than the quantum velocity. So, if V0 is slightly more than the phase velocity of the quantum force in the laboratory frame, in that case, in this moving frame, the electron velocity will be positive. So, the electrons will appear like moving here, they are going in this direction with some finite velocities. So, your electrons are moving in this frame with some finite positive velocities. What happens? The electrons in the accelerating zone will experience a forward force and they will quickly move out from the accelerating zone and go over to the retarding zone. The electrons in the retarding zones will be slowed down by this negative force, quantum motive force, and they will spend more time over there. As a result, more electrons cross from the accelerating zones to the retarding zones and less leave the retarding zone. So, there is a net bunching of electrons in the retarding zones, means there is a net retardation of charged particles of electrons and there is a net transfer of energy from the electron to wave if this condition is met. This is a mandatory condition, necessary condition. So, any electron beam moving faster than the phase velocity of the quantum motive wave, which is equal to omega upon k plus k w, will bunch in the retarding phase. This is a very important thing that is built in this concept of quantum motive force. And this is how the energy is gained by the radiation field. After all, quantum motive force basically is the radiation field and the regular magnetic field that are exerting this force. So, now what we do? We like to examine the energy exchange between the electron beam and the laser. So, let us examine the equation of motion of the electron. Equation of motion. I write down this equation for electron energy. Electron energy is actually not this is electron of equation of motion, rather I will not write for momentum, I will write for energy. Energy of the electron is defined as rest mass into gamma into c square. So, m is the rest mass, c is the velocity of light in free space, gamma is the Lorentz factor. I can write down this quantity, this equation of motion as, or energy balance as mc square d gamma by dt. This is the rate of gain of energy by the electron per second is equal to the net electric force or net force on the dot velocity, the electron gains. Now, there is only one electric field in the system, that is the electric field of the laser, and this could be the velocity which is the sum of original velocity V0 plus the velocity due to Wiggler plus the velocity due to the laser itself. And if you take the dot product of EL with those quantities, only the one that survives is this quantity. All other velocities turned out to be 0. So, the electrons gain energy because of this term, and it is useful to write this equation in terms for d gamma by dz, the evolution of the energy of the electron as the beam travels, so with distance, and this can be written as d gamma by dt multiplied by dt by dz, and dz by dt is the electron velocity, and electron velocity, initial velocity is V0 and then it slows down as the electron loses energy to the radiation field. In the limit when the radiation, the energy lost to radiation is small, I can replace it by simply 1 upon V0. So, dt by dz is 1 upon V0, the initial electron velocity, and d gamma by dt from this equation is equal to minus E EL dot VW upon mc square, and if you substitute these numbers, these quantities El and Vw, this turns out to be simply Fp z component of quantum motive force divided by mc square. So, quantum motive force is a very interesting thing here, in terms of which you can get the evolution of electron energy with the distance of propagation. Well, if you write down the value of Fpz explicitly, then this quantity turns out to be minus alpha cos psi, where psi is the phase of the quantum motive force, and I am defining psi as kpz minus omega t, and alpha is related to the amplitude of the quantum motive force and turns out to be equal to E square AW AL upon m square c square V0 gamma 0 kW. So, the energy the electron loses when alpha is and cos psi, they are positive, this product is positive. Obviously, alpha is positive for sure. So, cos psi has to be positive, only then gamma will decrease with z, and that is what we want. A decrease in gamma implies a increase or transfer of energy from electron to the radiation field. This rate of decay of gamma with z depends on laser amplitude, Wigler amplitude, and also depends on the Wigler wave number kW, besides the energy of the electron beam. We would like to examine the evolution of gamma and the phase of the wave, because psi depends for the particle. This is a quantity that depends on position of the particle and the instant at which you want to evaluate this. So, it will be better to write an equation for d evolution of psi with z, d psi by dz, and then you will get a coupled set gamma evolution with z in terms of psi and psi evolution in terms of maybe gamma or something. So, let us write an equation for d psi by dz. D psi by dz, if you differentiate this partially with respect to z, or not partially, fully, because z is a function of time. So, this is equal to Kp minus omega into dt by dz, which is like Vz. So, the phase of the wave as seen by the moving electron evolves according to this equation, and one can write Vz in terms of gamma by using this relation. By the definition of gamma, the Lorentz factor or relative gamma factor, this is equal to 1 upon under root of 1 minus V square by C square. And if I take V square to be like Vz square primarily, other components of velocity are weak, then from here I can get Vz by C is equal to, or square of this quantity is equal to 1 minus 1 upon gamma square. What we are trying to do now, that this set of equations involves gamma in a little complicated fashion. The equation for psi involves gamma through Vz in a complicated fashion, under root kind of thing will come there, and the equation governing gamma has cos psi on the right hand side. So, what we do, that if the energy transfer from the electron to the wave is rather weak, or small, then I can define two interesting quantities. One is the resonant gamma, means that electron, Lorentz factor of that electron that is moving with the phase velocity of the wave, so I call gamma resonant, is equal to 1 upon under root of 1 minus omega square by kp square. This is the velocity square of the electron if it is moving with velocity omega by kp and c square. So, we define a resonant velocity equal to omega by kp, the velocity of an electron moving with the phase velocity of the wave. Then the corresponding gamma factor for the electron would be gamma r. This is the resonant gamma factor. And we are expecting that your electron initially or later on will have energy close to gamma r. It may be slightly more than gamma r in the beginning, but not too much large. So, we will introduce a quantity gamma minus gamma r is equal to some quantity delta. So, we are saying that I can write gamma as gamma r plus some small modification, and this is a quantity of interest. We would like to learn if this gamma has some significant value in the beginning. As the electron moves in the system, then this gamma should decrease, and how much is the reduction, that we would like to estimate. So, what we are going to do, I would rather expand gamma as gamma equal to gamma r plus delta in this equation for Vz, and obtain the value of Vz in terms of this gamma r and this new quantity. One may note here that this Vz, if I put equal to Vp, then the right hand side is 0, because omega by kp is the phase velocity of the wave. So, any departure, if I had taken gamma equal to simply gamma r, then d psi by dz will be exactly 0, because then the velocity of the electron is the same as Vp. So, any departure in this or any value of this the right hand side will have a finite value only because of this gamma. And if you just simplify and do a little bit Taylor this binomial expansion, you obtain this expression. Let me just write the value. It turns out to be d psi by dz is equal to kp into gamma upon gamma r divided by gamma r square minus 1. This is the equation governing the evolution of phase of the quantum motive force as seen by moving electron, and it is proportional to gamma, the difference in normalized energy of the electron from resonant energy gamma r. And let me, so we have two coupled equations, this equation and the equation for gamma, d gamma by dz, which is equal to minus alpha cos psi. These two equations we need to solve. What we can do, we can define normalized quantities. Normally in literature, in FEL literature, people define normalized quantities. If the length of the chamber, interaction chamber or Wigler region is L, this is from here to here, this is Z equal to 0 and this is Z equal to L. So, this is the interaction chamber, interaction length where the Wigler exists, this sort of, and you are launching an electron beam here and you are launching a radiation signal here. So, suppose the L is the length of the interaction chamber, then I can define a quantity xi which is Z by L, normalized length, normalized to the length of the system, interaction chamber. And I can also define a normalized energy difference. Actually, if I put this gamma as gamma r plus delta, this equation becomes d gamma by capital gamma by dz. So, let me define a quantity p as normalized capital gamma, which is L into Kp into this increment in gamma from gamma r value upon gamma r into gamma r square minus 1. And let me also define a normalized amplitude of the pontomotive force, or the energy term, the driver term rather. It turns out to be, this is equal to L square alpha Kp divided by gamma r into gamma r square minus 1. So, alpha contains the amplitudes of the wiggler and the laser. So, in terms of this A, P and Xi, these two equations take a standard form, and let me write those equations. One is dP upon d xi is equal to minus A cos psi, this is the energy equation, and d psi by d xi is equal to P, this is the phase evolution equation. These are rather simple equations. What I can do from these two equations, I can divide the first equation by the second, and I can get this sort of equation: dP by d psi is equal to minus A upon P cos psi. I can take d psi on the right hand side and P on this left hand side and integrate. So, what I get is P dP is equal to minus A cos psi, and integrate on both sides, add a constant of integration here, C1. Once you integrate this, this becomes P square by 2. So, let me write this equation as P square by 2 is equal to minus A sin psi plus C1. C1 is a constant of integration, and it can be determined in terms of the initial values of P. Suppose I am launching in my interaction region electrons, obviously different electrons are arriving at different times. So, the electrons, but I am considering a mono-energetic electron beam. Suppose all the electrons that are coming here at any instant of time, they have initial value of this normalized energy P equal to P0. So, if I consider P equal to P0 as the initial value, and psi when an electron arrives, so suppose at the entry point, when an electron arrives at certain time, suppose the phase of the wave is, pontomotive wave is psi in, and initial momentum P is equal to initial momentum, initial energy, which is equal to P0. Suppose then C1 can be obtained from here, and C1 turns out to be equal to P0 square by 2 plus A sin psi in. This is the initial value of phase as seen by the wave as seen by the electron, pontomotive wave. Now, there is one thing interesting in here. Depending on the phase, the value of C1 could be less than A, bigger than A, or equal to A. If C1 is bigger than A and positive, in that case this quantity will always remain less than this. So, there are three cases of interest here. One case when C1 is greater than A. Please note one thing, the left hand side of this equation is positive definite because p square cannot be less than 0. So, right hand side should also be positive, which is possible because sin psi can take values from -1 to +1. So, when C1 is bigger than A and positive, in that case this right hand side will also be positive, and hence all values of the phase of the wave are accessible. All values of psi are permissible. And such electrons which satisfy this condition are called passing electrons or untrapped electrons. Passing electrons or untrapped electrons. In the second case, if C1 is less than A, in that case all values psi are not permissible because left hand side is positive definite, right hand side should also be positive. So, whenever C1 is less than A, all values of psi are not permitted. All values of psi are not allowed, means the electrons cannot move in a way that they can see different phases of the wave. Such electrons are called trapped electrons. And third case is the one that is the boundary between trapped and untrapped electrons, and that decides the separatrix. C1 is equal to A gives the separatrix. It is instructive to plot the separatrix and see what is the character of this curve P versus psi. When C1 is equal to A, I take C1 is equal to A, then this equation takes the following form. P square is equal to twice A into 1 minus sin psi. And let me plot this. So, if I plot this quantity, obviously one may recognize that P square is positive, but P can take negative or positive values. And if I plot here suppose I plot psi here and P upon A to the power half. Take the under root of this quantity, write plus minus sign there, and P by. So, the values that it can take is the maximum value of this quantity would be 2. So, 2 into 2 is 4. So, this I put a 2 here, this is my 2 here, this is 0 and this is minus 2, this minus 2, 0 and 2, and this is my phase is 0 here. Let me put pi here, then I put, actually let me little elaborate, this is pi here, let me call this pi here, then 2 pi is there, 3 pi is there, this is pi by 2 and pi is there. So, let me have a plot of this separatrix curve, separatrix. What you get? You will obtain when sin psi is equal to pi by 2, then P is 0. So, this is somewhere here I will get, and also when this is 2 pi plus pi by 2 somewhere here. So, you will get 2 zeros here and you will get a maximum here and a 0 here. So, this will be like this. And this will be 0 here, something like that. This is the curve of the separatrix. The electrons for which the initial conditions are such that C1 is less than A, they are trapped inside here and they go like this, their curves are like this and like this. These are called trapped particles. And the electrons which are outside this, they are like the electron, the trajectory here are like this. They are called passing particles or untrapped. What really happens? Initially, when you launch an electron beam, suppose initially you are launching electron beam with some finite energy. So, P has some value, suppose like this. Let me draw with a different color. So, the electron may be somewhere here. So, if the electrons are evenly distributed, means they are entering the wave at regular intervals. Some electrons, when they enter at a proper phase, they will be inside the separatrix and these will be trapped electrons. Some ones will be outside the separatrix and they are called untrapped electrons. So, the wave which is the ponderomotive wave will essentially trap some of the electrons, and these some of the electrons, when they move from larger value of energy P to a smaller value of energy P on this inside this separatrix, then they lose energy and they give it to radiation, amplifying the radiation. So, this is how in phase space the character appears like energy, electrons acquiring, losing energy and giving it to radiation. Let me make some estimate of energy gain, how much energy gain. This is the physics, that the electrons can be trapped within the potential well of the ponderomotive force and they can lose energy when they move on this curve from top towards the bottom. Now, let me examine in order to examine the energy gain, let me solve the equation of motion a little more carefully. This is the phase space plot, P versus psi. I am interested in knowing the value evolution of P with psi, the distance of propagation, normalized distance of propagation. So, what we have to do? For that, I need to solve the equation of phase evolution, because psi, if I can express in terms of z, the distance of propagation, then I can find out P as a function of z, and I do that iteratively. But I can always employ the expression that I just wrote down, that P square is equal to, for a trapped electron, P square is equal to 2 C1 minus 2A sin psi. This is the equation that I had written, a general equation. For C1 is equal to A, this became the equation for a separatrix. Otherwise, a general equation for particle energy in terms of psi. But this equation I have to solve in conjunction with the equation for phase evolution, which is d psi by d psi is equal to P. And it will be better if I write this C1 in terms of initial quantities, initial moment energy of the wave, of the particle, and initial phase. Then this becomes is equal to P0 square by 2. So, this 2C1 is like P0 square plus 2A sin psi initial. And from this is the value of 2C1. From this, if I subtract this quantity, this becomes simply this minus sin psi. So, this equation, if I take the square root of the right hand side, will give me the momentum, the energy of the particle at any position xi at which the phase is psi. When psi is equal to psi in, these two terms cancel and P equal to P0. So, this has to be solved in conjunction with this. So, P is a function of psi according to here, and I should put this in here and integrate it. But the problem is that because of the sin psi coming in such a complicated fashion, the integration is not possible. So, what people do, they solve this equation iteratively to different powers on A, treating that P0 is square is much bigger than 2A. Then you can binomially expand this, and when you do this, first of all, you can write this P by you carrying binomial expansion as this. This is approximately equal to P0 minus A upon P0 sin psi minus sin psi in, and then you go to second term, which turns out to be equal to minus half A square upon P0 cube sin psi minus sin psi initial phase whole square. This sort of expansion you get for P to different powers in amplitude of the quantum motive force. What we will do, probably we will have to wait till the next lecture. I will solve this set of two equations. One is a differential equation, another is an algebraic expression or trigonometric expression iteratively. First, I will consider to the 0th order if there was no laser. If A is 0, then P equal to P0, and I will find out psi is how much. Then I will consider that value of psi in here and use that value of P again to obtain new value of psi. So, iteratively I will evaluate P to higher orders in A square, and finally I would like to find out what is the energy that the electron retains at the exit point at xi equal to 1. Xi equal to 1 means z equal to L at the end of the interaction region, and this will be a function of initial phase. So, we have to average out over all the phases of all the electrons that are entering the interaction chamber, and that averaging will give you the net energy gain or energy loss by the electron, and we certainly want maximum energy loss by the electron, so that the maximum energy is gained by the laser, and we shall discuss these issues in our next lecture. Thank you.